So, question for you guys. When I click record, does the system ask you to authorize the recording?
That's not for me.
No.
Okay.
It just records.
Yep. Great. Okay. So let's get started. How do I screen share? Present. Entire screen. Okay. Great. So we left off at I think we left off at slide number 9, right? A puzzle. The following image has been modified by dividing the red, green, and blue values of each pixel by 5, 10, or 20. We don't know which color has been divided by what. It is up to you to restore the image to its original state. Is that correct? Is that the page that we left off on? I didn't get the puzzle, says Avni.
Yes.
Okay. So now I'd like you guys to volunteer so that we can solve these puzzles together, but primarily with the input from one of you. And we can learn together, how to solve these puzzles. I had a candidate for exercise number 1. That was Mark, if I remember correctly, who was saying that things didn't work for him. Mark, do you want to, would it be okay for you to screen share and show us your work?
Sure.
Okay, so I am unsharing my screen. You can share yours. And you may want to unmute yourself. Otherwise, we won't be able to hear what you're doing.
Oh, yeah. Okay.
Hi. I work.
Okay. Can you guys see?
Yep.
Yeah.
Yeah.
So like when I clicked the link over for the puzzles, it took me to this place. Yeah. So I was just trying to mess around with this thing, and I couldn't really get far because every time I hit run, nothing really would happen.
I haven't tried that page. I've tried the code in the slides. So in the slides, it works. So what we could try doing is use the slides instead.
Okay, how do I open the slides?
Click on for loops, right next to the date. 3/20/3/20. Click on for loops. Lecture 5. Great. And it was slide 9. So.
Okay.
Okay. There you go.
Oh. Okay.
So click run. Let's see if that works. It should.
No. Oh, there you go.
Oh, there you go. Okay. So we can recognize that it's a banana, but we certainly don't see it well. So can you help us recover a, good, healthy-looking banana from that image? And can you explain what you're doing while you're doing it?
It says so. It says the each of the values, red, green, and blue, have been divided by a 5, 10, or 20. So you can undo that operation by multiplying that by either 5, 10, or 20. So that's what I'm gonna do.
Okay. Let me ask everybody else on the chat, what do you think is the right factor for each of the colors?
What do you mean by factor?
We have to multiply
The RGB values.
Yeah. Multiply each RGB color by a multiplier.
Some number.
Yeah.
Exactly.
Yeah.
Exactly.
So there seems to be some agreement on red being 20, green 5, and blue
10.
Somebody is saying blue 20. Amelia is saying blue 20. However, if we multiplied blue by 20, then we would be missing the 10. Right? Red 20, green 5, blue 20. Hello? Mark, you there? Can you guys hear me?
Yeah, I can hear you perfectly.
Yeah, we can
Yeah.
hear you. I think he's just frozen. I'm gonna go
Okay.
troubleshoot it out on his computer.
Are you guys in the same place?
Yeah,
Yeah,
the
it's
brothers.
just. I'll go.
Usually, usually the brothers.
Yeah. Okay, well, let's see if they can regain control. Oh, there you go.
Extra pages.
Is it work now?
Yeah, it's working. It is
Uh,
working.
It works.
Need to go
Right,
Wi-Fi, man.
Red, blue.
Mark,
Hello? It's working, right?
Yeah, we're seeing your screen.
Yeah, we can see your screen. Go ahead.
Okay. And how much was blue by? Was it 5 or I think it was 20 or 10? 10?
I think. Don't they mean respect? Oh, okay. We don't know which color has been divided by what. Okay, I see.
We don't know. So the
Okay.
point of the puzzle is to try different combinations and see which one
Okay.
works.
Okay.
And if you screw up with coefficients, I use the term factors, but really coefficients, then you get a very odd-looking banana. Still looks like a banana. Okay, you've got a mistake.
Where did I mess up?
Get red should
I
be
know.
immediately followed by.
parentheses.
Oh yeah. Wait, what?
And Warfighter says add open close parentheses. Yeah. And I
There you go.
saw it. There you go. We've got a healthy looking banana.
Woohoo!
Very healthy
Well
looking
done.
banana.
Hey, do you know why? Did you explain why you have those parentheses after the words get red, get blue, get green?
I did not, and I was thinking that might be something worth explaining.
Yeah.
Why do you guys suppose we need parentheses after get red, but not necessarily after some other words that may be associated with pixel or with image?
Because you need closed parentheses.
Because I
To
think the value would go inside the parentheses, and when you multiply it, it would multiply that value by the other number.
Well, but look, the point is, pixel.getRed, it would seem like it would make sense even without the parentheses, but you've had to add parentheses after getRed, and there's nothing in them. So if you use parentheses the way we use them in math, just to determine order of operations, they don't seem to make sense here. So Sanjay's question is, well, why do we need them? And the answer is, we use those parentheses in the same way they're used in the context of functions in math class. Have you guys studied functions in math class?
Yeah.
Yeah.
Okay, let me go back to screen sharing myself. So functions are mathematical objects that take parameters or arguments and return a value, right? They do some math and they return a value. And the parentheses are what we use to indicate that an object is a function, and Sanjay is saying f of x, right? F is the function and x is the argument. And that's the syntax that's been adopted in many programming languages, but not all of them, to indicate that something is a function and something else is an argument, and that the function ought to be called on the argument. And you guys should be seeing my screen, all right? I will take that as a yes. And then we've got another mystery. If I click run, we don't see anything. Whereas in the previous slide, we had a healthy looking banana. Or actually, we had a banana, not very healthy looking, but we had a banana. Now it looks like we don't have anything. So that's another great mystery for us to solve. I can go ahead and show you, or if I have a volunteer, I'd be happy to give you guys control. I will
I
take the
think
line.
I can do it.
Okay. Who was that?
Adam.
All right, Adam. If I don't have any other volunteers, I don't see any volunteers here. Okay, Adam. Avni is asking, like, why does the colors work? Why does it work? Colors, numbers. Avni, what do you mean by that?
Alex, I'll take care of
my
that.
screen?
Why don't you work
Okay.
with Adam? I'll take care of
Did
that.
Okay,
you
okay.
Yeah. Can you guys see my screen?
No.
Yeah, we
Ah.
can see your screen.
Can you see
We
my
can
screen?
see, no, sorry, we can see you, not your screen.
Can you see the
Now-
screen now?
Now we can see your screen.
Okay. So basically it says the green and blue values are random values. So we don't need them. So we just do pixel dot set green, and we can do 0.
Mhm.
And we can do pixel dot set blue 0. And then for red, the red values have all been divided by 10. So we can do pixel dot set red pixel dot get red. Then we can multiply that by 10 because that's what we need to multiply it by. And then it should show an image.
Okay.
Maybe I'll try through the
Copy and paste it rather than doing it from scratch. Just copy and paste your code into, yeah, exactly.
over here.
It was page 10, I believe.
Yep. Oh,
So what is it telling you? Okay, it's a very red day in San Francisco today. So
Yep.
why is it so red? Right, you have removed all the noise, which is fine. So now we can recognize what the image is. Why is it so red?
because red is the only value that's acting upon it.
Okay, that's right. You set everything else to 0. Now, what if you wanted a more natural looking image? What would you do?
Maybe I could try adding green and blue values.
Okay,
So, or I can convert it to grayscale potentially.
okay, and how would you do that? Grayscale seems like a good idea.
I could do, so I have to get pixel dot set red, and I would have to get that red pixel dot get red, and then I would have to set green and blue to those exact same values.
Okay,
So I wouldn't need this. I would just need pixel dot set green, and then I would need pixel dot set blue, and then that should set the red values to the green.
let's see. Let's try. Set green called with 0 values.
Called with 0 values. Oh,
Okay. Anybody on the call have an idea what's going on here? What's the problem? And how do we solve it?
Maybe change the numbers of set green and set blue, which are currently 0.
oh wait, maybe I have to put the pixel dot get red inside of there.
Yes. right? Just like you're doing for set red, you have to pass a value to the set function, right? Rather than passing the set function to something else.
Yeah. So basically, I don't need any of this or this. I don't need this.
It's pretty clever, though. Good job. Yeah, you're thinking the right way.
Yeah. Everything is black. What's going on? You're missing something. Which you had earlier, right? When you had the red Golden Gate Bridge.
Oh yeah.
Nice. Hey, look at that.
Yeah.
Okay. Yeah. And I'm curious, why are you multiplying the red only once by 10? It would seem like, because you're multiplying the red color or, the red channel by 10, not the others, this should still look very, very red. Like your picture should still have a dominant color, right? The red color should be dominant. Why is it not?
Because it goes in sequential order, so it multiplies it by 10 first, and then it uses that same value that's multiplied by 10 to set the other ones.
Very correct. Absolutely correct. Wonderful. So let me take control.
You may want to
again.
explain that again, Alex, just to walk through it for everyone.
Yeah. So what Adam is doing, and now we don't have his code on the screen anymore. Can
Hey,
you
Adam,
pull
put
it
your
back
code
up?
back. Yeah.
Yes, thanks. So what he's doing here is he's first setting red, right? And what is he setting the red value to? Well, he's taking the current value of the red channel, he's multiplying that by 10, and then he's storing it back into the pixel. So he takes information out of the pixel, multiplies it by 10, puts it back into the pixel. Then he operates on green, and he says, well, now I want to set the green color to be the same intensity as the red color, which he changed. It's not the same as in the original image that we pulled out of the website. This is the modified red that has been multiplied by 10. And then he does it again for the blue. So even though the parameter that he is passing to set green and set blue looks different, because he doesn't have the multiplication by 10, effectively, he is passing the same value. It's a little tricky to read this way, right? It's absolutely correct, but it's a little tricky to read. So let me take control, and I will show you another approach to solving this problem. And are you guys seeing my screen now?
Yeah. I can move it up.
Okay. Now, which one is the right one? Here you go. Okay. So this is how I did it. Oh, gosh. Okay. See if that works. There you go, Golden Gate Bridge. So what I'm doing here is I'm creating a variable. Let r is equal to pixel get red times 10. I'm doing it once, right? I'm not calling get red many times. There is an aspect of readability, and there's an aspect of computing cost. Every time you call a function, you're asking the CPU to do work. And it might not be a ton of work, but it's it's work. So the CPU will have to look up the function, start executing the function. The function contains instructions to go and get information out of an object. That information is then returned, multiplied by 10, and then you get it. So if I call getRed 3 times, I'm paying 3 times the price of getting that information out of the pixel. Again, it might not be a lot of cost. It might be a very small fraction of a second. But if we're doing this millions of times on a large image, it adds up. So I'd rather do it once. And creating a variable here allows me to do it just once. So I'm creating a variable called r, and I'm setting the value of that variable to the red value of that pixel multiplied by 10. And then instead of having a complicated expression where I have a function called inside a function call, I'm just setting the red to r and then setting the green to r and the blue channel to r. So now this is a whole lot more readable. If I click run, there you go. A nice and gray Golden Gate Bridge. Does this make sense? So
Yeah.
the takeaway here is to use variables, right? To use variables to capture intermediate results that you will be using again. And sometimes, even if you don't plan to reuse that value more than once, it's still interesting to have it in a variable so that you can read through your code, and especially if the variable has a good name. Let's give it a better name. Red value. Okay, now this really has a good name. Next time I read through it, I will know what this means. Okay, so this doesn't change the meaning of the program, but it changes the readability rather significantly, and it makes it a little bit faster. Okay, which is nice. Okay, let's move on. This doesn't matter. Grayscale. Well, we've already done some grayscale work, so I think we can just go get it. Or is anybody interested in presenting and showing us how to compute grayscale out of this nice colorful image? Going. Okay, I'll do it.
I
Do you have a
screen share, but
do I?
yes.
I'm sorry. My dog is barking right now. So what did you say again?
I can't screen share it, but I have a guess for it.
Okay, tell me how you would plan on solving this problem.
Maybe set all the colors to the same, or is that white?
I can try.
Who is that?
Adam again.
All right. I would rather have other volunteers, but by all means, Adam, take control and do it.
Okay.
And please, guys, do volunteer. Do take the opportunity to try out your programming skills, and you'll get the help of everybody else on the line. Nobody will make fun of you. Of course, if you don't do a good job, we will send a progress report to your parents. But hey, that's just a price to pay.
For some reason, it's not letting me share.
Maybe I have to unshare. Go ahead.
See, no, it's still not letting me share.
Okay, now that's interesting.
That's weird. Yeah, for some reason it's not letting me share.
Okay, that is odd. So I don't want to take too much time, and we do have a lot of material to cover.
Yeah.
So I'll do this myself. So let's take the code from here. You guys see my screen?
Yep.
So the idea here is to compute the average of red, green, and blue. Now, when you convert an image, a color image, into a black and white image or a grayscale image, you want to take some combination of red, green, and blue. Because if you only used red or only used green or only used blue, well, what if the image has a lot of blue light in it or a lot of red light, but not something else. It's only red but no green, and you had picked green as the source of information, then you wouldn't have a good grayscale image. So we take some kind of average. What I'll show here is, quite literally, no, wrong code. Quite literally the average of the three colors. This is probably not the very best combination of colors, but good enough. Okay, and you can see that I'm using variables a lot. I like variables. Variables are my best friend. So let R is equal to pixel get red. Let G is equal to pixel get green. Let B is equal to pixel get blue. So now we have the variable R that contains the red value of that pixel. G contains the green value of that pixel. B contains the blue value. Now I can do the average. I can compute the average of the three colors. How do you compute an average? Well, you add up the three numbers and divide them by 3. Okay, so this is the grayscale value that I want to set in that pixel. I'm calling that average. I'm creating another variable called average that contains literally the mathematical average of red, green, and blue for that pixel. Now I can call set red average, set green average, set blue average. Does that make sense?
Yes, yeah.
Okay,
Yeah.
Run. And lo and behold, we have a beautiful black and white picture of flowers.
Quick question.
Sure.
So if you've already taken the average of all 3, why did you do pixel set red average for all 3 colors?
Because on this line of code that I'm highlighting now, I'm only doing the math. I'm literally only adding up the 3 numbers and dividing the result by 3. That doesn't change any pixel, right? It doesn't affect pixel at all. If you see, there is no reference to pixel on this line. I'm neither getting information out of the pixel nor sending information to the pixel.
So then for pixel set red, if you're saying average, let average equal blah, 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 then how does plus G and plus B affect it?
Well, bear in mind, I've done the math before calling set red. Let's imagine that we have a pixel whose color values are, say, 50 and 50 for red, 100 for green, and 150 for blue. Okay, so we've got 50, 100, 150. And now we've stored 50 in R, 100 in G, 150 in B. Now we compute this line of code, right? And again, here we're just doing the math. So help me out here. We've got 50 plus 100 plus 150. Okay, so we've got 100. 50 plus 100 plus 150. Total is 300. Divided by 3 is 100. So now AVG is a variable whose
Oh yeah, that makes sense now.
value is 100. So now we call set red on AVG, but AVG is resolved to the value that the variable references. Okay, the value that the variable references is 100. So we're calling set red on 100. And then we do it again, set green on 100, set blue on 100. And so we get the same light intensity for all 3 primary colors. Okay, but that light intensity has been computed as the average of the red, green, and blue values of the original image. Okay, can I move on?
Now. Yes, thank you.
Is everybody good with that? I'll take that as a yes. So let's add some new tools to our toolbox, okay? One is interesting, set RGB. So if we use the set RGB, we could have made the code here a little bit shorter. Instead of calling 3 functions, I could have called just one function, AVG, AVG, AVG. Okay, that's red, green, and blue. Lo and behold, same result. Okay, so that makes things a little bit faster and easier for us when we're modifying all 3 colors. Then we have a powerful construct that is completely new, which we didn't have before. Image get neighbors of pixel. Okay, now image get neighbors is a method that's attached to the image object. And basically, it's a message that you send to an image object to tell it, hey, give me a list of all the pixels that are neighboring to this pixel. What does it mean for a pixel to be a neighbor of another pixel? Well, you remember that an image is made up of a lot of pixels that are arranged in a square matrix, right? We've got a certain number of columns, a certain number of rows, and so we have, a square matrix of pixels. For any given pixel, there are going to be some pixels that are touching it. So how many pixels touch any given pixel in an image? Well, let's imagine we're looking at a pixel in the dead center of our image. It will have, yes, please.
8?
Yes, right? 3 on the left, 3 on the right, one above, 1 below. So there are 8 neighbors to a pixel that is in the middle of the image. But not all pixels are in the middle of the image. Some pixels are on the border, and they may lack neighbors on one side or on 2 sides if they are in a corner. Okay, so there can be 5 neighbors, 1 above, 1 below, 3 to the right, or again 5, 1 above, 1 below, 3 to the left, and so on. In the case of a corner, we will have how many neighbors? We don't have the top row, we don't have imagine the top right corner, we wouldn't have the top, we wouldn't have the right border, we only have the bottom left corner of the square of 8
3.
pixels, right?
I think 3.
Exactly, 3. And image count neighbors does exactly what we've just done in our heads, right? It does the math. It counts how many pixels neighbor a given pixel, so that you can look at count neighbors to determine, for instance, if a pixel is at the corner of an image or on the side or in the middle. Now, there's faster ways and cleverer ways to check whether a pixel is on the edge of an image, but this is one way. So we'll use these building blocks in the next challenges. This is a slide with a little bit of review on for loops. I think we're all clear on this. For basically the way we're using the for loop, we're using the for each variant of the for loop. It basically means run one or more instructions, exactly the same instructions, for every item in a collection of items. In our case, for every pixel in an image. So now things start getting really, really interesting. Okay, and unfortunately, I think the exercise that we are being offered doesn't do justice, or the image that we will see for this blur filter won't do justice to the exercise. But this is a very, very interesting problem. You guys know about Photoshop. You might have Photoshop at home or something like it, and you probably have played with the filters that allow you to change an image, right? To make it blurrier or sharper, or or other that allow you to modify the image in many different ways. Why don't we implement our own blurring filter? Okay. So what's the idea? Well, in order to blur an image, we basically want to, it's kind of like if every pixel were a drop of ink, and we dropped the ink in a glass of water, and the ink started spreading. And we want the ink to spread, but we want to control how much it spreads. And so after a little bit, the ink will have spread by a certain amount, and then we take a picture of what we have in the glass of water, and that's the result of our blurring algorithm. That's basically what blurring does. So we will be looking at the neighbors, right? That's why we have that get neighbors function, right? This function here, get neighbors. We'll be looking at the neighbors of a pixel, and we will be allowing the color information from each of these neighboring pixels to spread inwards, to spread towards the center pixel that we're looking at. And the author of the slides is telling us, note that we need a second image. Why do we need a second image? What does it mean we need a second image? Here's the code that they have set up for us. IMG, new simple image, result, new simple image. And so we're using two different images to run this algorithm, right? We will take information from one image and use this information to modify the second image. Notice that the two images that we're working with are exactly the same, right? I have them open up here in my tabs 3 and 4. As you can see, I'm flipping between the tabs, but it's exactly the same image. So there's nothing between these two files. There's no difference between these two files. Indeed, we could probably just use the same file altogether, and it would work just fine. The point is, they want us, I don't know why this one doesn't, oh gosh. Excuse me. Does that work? Okay, I'll have to figure out why this is not working now on my computer, but the idea is we need to use two images because we're taking information from one image and modifying another. If we were modifying the same image that we're taking information out of, then we couldn't count on the values of the pixels being correct, right? Because we're modifying them at the same time. So you want to take information from an image, and then you want to have a different image somewhere else in the memory of your computer to store the result of your calculation, right? Otherwise, you'd be stepping on your own toes, so to speak. Okay. Do we have a volunteer to try out this algorithm? Do you guys want me to do it? There you go.
Something's up with that. Yeah, I don't know what's going on.
What's that, Sanjay?
So I'm not sure why it doesn't work either. It should work.
Well, apparently there is a reason they used two different copies of the same file, right? Somehow, if I use the same image twice, it doesn't work. This is very odd. And guys, bear in mind that we're using JavaScript as the language, but we're using the specific library that is made available to us by the authors of the class. And so I really don't know what dark magic they're using, such that if the result is loaded from the same image, somehow, things break and it can't, we can't use it anymore. So I don't know why, but I can show you how to compute the blurring of this image. Like I said, I am unsatisfied with the fact that we can't blur to a point where we can really notice it. But at least I can show you the algorithm. Okay. Does that work? Notice that it's taking some time now. It's actually doing a lot of work. And lo and behold, we've got two copies. That's not what I wanted, but we'll use IMG up top as the reference, the one that has not been modified. Unfortunately, that's way too big. IMG set zoom 0.5. Notice that when JavaScript is working, I can't click on anything. Okay, so it worked. It worked. Unfortunately, I'll try zooming in. I can't even zoom in.
Maybe you can just stretch the page, yeah.
That's what I'm trying to do. There you go. No. Yeah, it's the fact that scrolling with the mouse causes the images, like the slides, to change, makes it very, very hard to use these slides. But you know, we're still thankful to Ashley Taylor for sharing them with us. It is.
Zoom?
Let me see. The fact is, I can zoom, but in practice, nothing happens because the code of this page is it adapts to the size of the window. And changing the zoom of the window effectively changes the size of the window as reported to the HTML and the JavaScript. And so I don't really get any effect. What I want to do is use Chrome's ability to zoom in through the gesture, the macOS gesture, where I pull my fingers apart on the trackpad. And that would work. But the problem is then I don't see the page anymore. I don't see the right page. So you'll have to trust me that the one on the bottom looks just a wee bit blurrier. Okay, the whole image is blurry, so it's kind of hard to notice any difference, but it looks a little blurrier. Unfortunately, that's kind of what we have to, what we're working with. So you'll just have to trust me that it does look a little blurrier, but let's focus on the algorithm. So we're loading the two images. The reason we're loading a second image is just as a way of getting a separate image object that we will be writing to. It's kind of a clumsy way to do it. I would much rather use some method for duplicating IMG, creating a separate copy of IMG to work on. But that doesn't seem to work with this code. So we'll use new simple image and we'll load in a different copy of the JPEG file, and that'll be the value that we write to. So we will discard the information in PoppyBlur altogether, and we will write every single pixel by doing some math on the original image. And here's what we do. So for every pixel in the image, okay, what do we do? First of all, I want to know where the pixel is. So I need its x coordinate and I need its y coordinate, and you'll see why we need it later, right? And intuitively, we will need to know where the pixel is because we will want to do something to the pixel of the other image in the same position. So now I have to start computing the average. The average color, the average red color, the average green color, the average blue color within the neighborhood that this pixel is part of. And so I want to add the value of the red color, the red channel of this pixel, plus the red color, the red channel of all its neighbors. And similarly with the green, I want to add the green of this pixel to the green of all its neighbors, and the blue to the blue of all its neighbors. And then I'll be taking an average. Okay, so I'll be dividing the total by the number of pixels that we've processed. How many pixels will I process most commonly? Well, most pixels are in the middle of the image, and they have, like we said, they have 8 neighbors. So 8 neighbors plus the pixel itself is 9 pixels. For the most part, we will have 9 pixels that we're taking the average of. And on the borders, we don't have 9, we have a little bit less, and in the corners, we have even less. So the idea is to create some running totals, a total for red, a total for green, a total for blue. I initialize these totals with the current pixel, the one that I'm looking at, that I'm focusing the attention on. And I start counting the number of pixels that I processed, right? Right now I processed 1 pixel, the current one. Then I start looking at all the neighbors. For every neighbor in the list of neighbors of this pixel, what do? Well, I do some more math. I want to change the value of total R. Here I have defined the variable and given it an initial value. Now I'm changing the variable. That's why I don't have let anymore. Let creates the variable. Here I'm not creating the variable. I'm using a variable that was already there, right? That was, that I had created up here. So I'm taking total R and I'm setting it to a new value. What's the new value of total R? The new value of total R is equal to the old value of total R plus the red value of the neighbor. And I'll do that for green and blue as well. And then I count the number of pixels, right? I change the value of the variable called num of pixels, and I set the new value of num of pixels equals to the old value plus 1 because I have processed one more pixel. So what I want you to take away so far is that we have created variables and then we have modified variables. That's the first time that we see that, right? Creating a variable and then modifying it. And we modify total R, total G, total B, and number of pixels once for every neighbor. Does that make sense?
I got a question. Do you have
Sure.
to, you have to put let, or could you define the variables ahead of time without using the let, or does JavaScript make you use let?
So JavaScript is an intricate language because it's very old. And the original versions of JavaScript were completely stupid in terms of the design of the language. And so over time, the language has evolved and it has become a little bit friendlier and nicer and easier to read and understand. Let is a fairly recent addition to JavaScript. In the original versions of JavaScript, you could just do this, right? And JavaScript would say, well, I've never seen X before, so probably what you really want to do is create a new variable. Okay, I'll create a new variable for you. That actually lends itself to a whole lot of mistakes. Every spelling mistake, JavaScript will say, not a problem. Instead of X, you want it, what's the letter that's right next to X? Say that I had typed a Z by mistake. JavaScript would say, that's totally okay. I'll create a variable called Z for you. And then elsewhere in your program, you use X because X was supposed to be the right name, and things fail spectacularly. So modern versions of JavaScript have 3 different ways to create variables. I will not go into them. Let's just stick to let, okay? So my convention is when you create a variable, use let so far, right? And we can get into, we can get fancier than that, but for now, we'll create variables only with let.
Hey, Alex,
Okay?
do one thing. So there's an outer loop here, which is for each pixel from the image, right?
Yep.
There's an
Outer
inner
loop.
loop that is grabbing the neighbors.
That's a very good point. So
And
we
then,
have, go ahead.
No, and then the last line of this for loop, of the outer for loop, the last line of the outer for loop is taking all this computation and setting it in the result pixel.
Right.
That's so all this math inside is ultimately to change the results. I mean, that's kind of obvious.
Yeah,
right?
That's a very good point. So here, after having done all the math,
what are you printing in the end?
we're printing both image and result.
And the result, yep.
Okay, so the one on top is the original. The one on the bottom is the modified version.
Yeah, they look kind of the same through the GVC.
They look basically the same. The point is, in order to notice filtering at the level of only one pixel on each side, you really need to zoom in a lot, or just have an image with a much smaller number of pixels. For instance, if we applied this code to the X image, the small 10 by 10 image that we were playing with a cross on it, we would actually see it nicely.
Yeah, I think even here you can see it. Like if you look kind of on the left-hand side, look at the green on the upper one, and then you look at the same area in the lower one. The lower one is kind of whitish. It's more white than the one in the upper photo. Does that make sense?
I think I noticed it a little bit more on the border between the petal and the background. Right? It does look a little bit blurrier on my screen, but I don't know that it's that it comes across through the screen sharing protocol.
It looks a bit blurrier.
Let me see if I can get.
Can you actually just change the name of the file and just use the one with the X?
I tried. The problem is we need 2 different images, right? And what I tried doing basically earlier is use the same file for both image and result, and that failed. So really what I need to do is create a copy. if that worked. Let's see. Simple image. That's a simple image function. Dot prototype. Don't look, right? This is not what we should be doing right now, but get index, set red, set green, set blue, set alpha. The idea, what I'm looking for, and I can't find anything here, is to create just a duplicate copy of the image so that I don't have to read, read the image again. And that would allow me to use the x.png and copy it. Like I said, can't really do that.
Yeah, I don't know why that should have worked.
Well, we could try. Let's see, x.png, and yeah, it's just result equals x.png. Let's comment this out. And then we have to use result here. Let's see what happens. That's going to be very small. We don't have.
Don't you need a zoom function?
Yeah, set zoom 20 maybe.
Yeah. Hang on. Problem is, I am probably not printing the right stuff. That is very interesting.
It's probably
that is very interesting.
Probably some memory thing in this implementation. Who knows?
No. I think, well, now it's working. So there you go. So you can see, I don't know why it's kind of overlapping. Set zoom.
I think the number of pixels in the x.png is pretty small.
Let's see if we do it this way. Okay, now this is really, really small. So let's zoom it up by a factor of 20, I believe we're using. There you go. There you go. So as you can see, this is not your regular x.png, right? The regular x.png would be black and white. It has become a little, greenish. Let me remove this. There you go. That's the original. And if I add back the code for the neighbors, I get this. Now, why do I get this weird color? Well, the problem is we are, like I said, we're stepping on our own feet. We're modifying the same image that we're reading information from. And so that's not correct, right? We really should be reading information about the pixels from an image that we're not touching and writing information into a separate image that we are modifying. That's kind of what it's the best I can do right now based on the limitations of the environment that we have here. But as you can see, we are obtaining this averaging effect, which is really what we are after. So far, so good?
Yep.
Okay, I want to switch to the next topic. So recap, for loops allow us to quickly and powerfully edit images. Well, more than just that, fundamentally, they allow us to do something for every element in a collection of elements, okay? Now, first question that I have for you guys. Are for loops all that we need to have a fully featured computer programming language? Can we do everything we may ever need to do using the tools that we have so far? I'll give you an example.
No.
There's a use case for programming where we want to, say, allow a user to view or not view a certain movie on Amazon Prime. Well, the question, for the Amazon guys, the question is, has the customer paid to see this movie? Yes or no? And if they have paid, then they get to see it. If they have not paid, then they don't get to see it. But we might want to do something else instead. We might want to show them a screen where they can pay. If they want to pay, then we'll happily take their money and then show them the movie. So the question is, how do we... Go ahead. Okay, how do we tell a program to do something or not based on some condition?
Hey, Alex,
Well,
why don't we take a break now? Before, like, we're at 6:45.
Perfect time.
Take a 5-minute break, come back, and then we'll do this. This is actually pretty quick today.
Yep.
All right, everyone, take a 5-minute break, come back.
Chewing.
Hey, can you send out the text, the code that, Alex, can you send out the code that you're using so we can play with it?
Sure.
Just
I
paste it in
can.
the chat window.
Yep.
That window, maybe?
Yeah.
Yes, let me do that.
Sorry, Alex, I have geeky friends.
That's totally fine.
This guy is the worst. He goes to Holy Spirit.
Means I have nothing else to do because we can't go to mass. So hey,
There you go.
New
Is that
religion.
complete? That's not even complete. It looks like there's a limit on the number of characters that I can paste. So what I should do in reality is paste it to the shared. This is
Google
not even
Doc?
the right place, right? Where is the Google Doc?
Awesome.
There you go.
Thank you.
I'm going to turn on the pizza oven. Be right back.
All right. Did you guys all have access to the shared file? I see there's a lot of people logged into it, so probably yes.
All right, shall we? Let's go.
Let's do this. Okay.
Okay, Google, stop.
Go back to screen sharing. All right. So how do you ask JavaScript in particular to do something or not based on some yes or no question? Okay, yes or no questions are called Booleans, or their value is called Boolean in computer science. A Boolean and binary are kind of like, they're synonymous, or at least a single binary digit, a 0 or a 1, is a Boolean value. Multiple binary digits, like a long binary number, would not be Boolean anymore. But true and false values, like values that can either be true or false, are called Boolean. So how do we build software that makes a distinction between a yes or a no condition and does something in the yes case and maybe does something else in the no case? We use an if statement, right? Very clever choice of name. The idea is to write a block of code, not a function or a function call, but a whole block of code where there's a condition called, well, the condition. And then there's a body of the statement that contains all the instructions that we want to execute subject to the condition. So here's an example. Take a look at this code. Why don't you tell me what you think it does? Bear in mind that this x.png is our friendly little white cross on a black background. So let's read it together. For every pixel in the image, if the red value of the pixel is equal to, notice the double equal sign, is equal to 0, then do this stuff. What does this stuff do? This stuff is set the red, green, and blue values of the pixel to 255 for red, 150 for green, and 0 for blue.
Hey, Alex, can you comment on this double equal thing? What is that double equal? I've never seen that before.
Yeah, so you guys remember that we've used the equal sign in the let variable definitions to initialize the variable to a certain value. And we've used the equal sign to set the value of a variable to something else. Let's go back to, for instance, this code. So here we have the equal sign in the context of a let instruction that creates a new variable. Okay, so we're saying let x become equal to or be equal to pixel.getX. And later on, well, not for this one in particular, but for this one, so let total r equal to something, be equal to something, and then later we use a sing variable name. Total r becomes equal to total r plus neighborhood get red. Here, we're not interpreting equals in the same way that we do in math, right? In math, this would be an equation, and we would be solving the equation by canceling total r on the left, total r on the right. We'd get 0 is equal to 0 plus neighbor get red. And so we'd conclude that, get red is 0. No, that's not what we're doing here. Here, the equal sign means set. It either means initialize. In other words, I'm giving a definition. I'm defining x to be equal to pixel.getX, or later on, I'm changing the value. I'm saying from now on, total r becomes equal to total r plus neighborhood or neighbor get red. Okay, that's a single equal sign. And this is JavaScript. Other languages do it differently. But in JavaScript, the single equal sign basically either creates a variable here or changes the value of a variable here. It's not an equation. It's either a definition or an instruction to change a variable. Now here, we need something completely different. We're not setting the value of something to 0. We're asking the question, is it 0, right? And so we need something that reminds us of the notion of equality, because that's what we're asking. We're asking, is this equal to that? But if we use the single equal sign, it would have a complete different meaning. It would mean in JavaScript, make the thing on the left equal to the thing on the right. So in JavaScript, they've adopted, in many other languages as well, the double equal sign as a way to check whether things are actually equal. So this statement means, is the thing on the left equal to the value on the right? Yes or no? And the answer is a Boolean. The answer is yes or no. Or, more formally, the value, the result of this operation is true or false. And true and false are two different values in JavaScript and in most other programming languages as well. Does that make sense? I'll take that as a yes. So here we're asking the question, is pixel get red equal to 0, yes or no? And that's the first step, right? We're executing the condition. The condition returns a Boolean value, a yes or no value. And then we execute the if statement. If the condition is true, then execute the body of the if statement. Now, let's try to understand what this is going to do, and then I'll click run. But first, let's try to understand. For every pixel, if the red value of the pixel is equal to 0, in other words, if it's a black pixel, we know that in the original x.png, the pixels are either black or white. So if the red value is 0, it means that it's a black pixel. So if it's a black pixel, then color it to a different color. So by reading the code, I know that this piece of code, this piece of JavaScript, will change the color of the background of the white cross. The white cross will still be there, but the background will not be black anymore. It will be red 255, green 150, and blue 0. So I'm guessing it'll be some kind of orangish. And there you go. Questions so far? Okay, so the takeaway again is the if statement has two parts, the condition and the body. The condition is a piece of JavaScript that can be interpreted as a yes or no question. Is thing on the left equal to thing on the right, yes or no? If the answer is yes, then you execute the body. If the answer is no, the body is skipped. Okay, and we would go ahead and execute something else down here. Blah. Okay, I don't want to leave this here because obviously it doesn't make any sense in JavaScript, but that's the idea, right? If the condition is not true, we skip the body and move on. Okay. Well, what kinds of conditions do we have access to in JavaScript and other programming languages as well? Most commonly, we have access to the same kinds of operators that we have in math. So we've already seen the equals operator. Is the thing on the left equal to the thing on the right, yes or no? We also have an interesting and imaginative way of writing not equals, okay? In math, we would probably write the double, the two lines, the equal sign, and then cross it, with a diagonal line. That symbol exists in modern fonts, but it's certainly not common on a keyboard, so it would be hard to type. So instead of having the equal sign with a slash through it, we use the exclamation mark followed by the equal sign. And the exclamation mark in many programming languages means not. It means the negation of something. Okay, so we're basically saying not equals, okay, with the exclamation mark followed by the equal sign. And it's a yes or no question. Okay, you can't make something not equal to something else, right? The equal sign by itself means make the thing on the left equal to the thing on the right. But you can't have any kind of interpretation of the symbol where it changes things. It's really just a yes or no question. Is the thing on the left not equal to the thing on the right? Yes or no? And yes means yes, it's not equal. The other things that we have access to are the relational operators. In other words, the ones that establish an order between things. Greater than, less than. This is kind of interesting. Again, it's based on the fact that we don't have all the characters on a keyboard that we would use in a math class. So this is the greater than or equal to operator. Now, greater than or equal to. And here we have the less than or equal to operator. Okay, so if we call 5 greater than 3, yes or no? Okay, we use this operator, 5 greater than 3, yes or no? What would JavaScript return? JavaScript would return true. 5 is greater than 3. How about 3 greater than 5? Yes or no?
No.
JavaScript would return no. What if we told it 5 greater than or equal to 5? Oh, sorry, not greater than or equal to, greater than 5?
No.
JavaScript would return a no. That's right. How about a thing, let's use this one for an example. How about, 3 exclamation mark equals 5? Yes or no?
Yes.
Yes. That's right. Yes. Okay, so you get the idea. There's other things that we can use to generate Boolean values that are appropriate in the condition part of an if statement. But for the most part, the other things that we could be using are functions that internally use these operators to make a decision and then return a yes or no. Okay, so at the heart of every Boolean condition, there is something like this to generate the Boolean value. So once we are using an if statement, we will be operating only on the pixels that pass the test. So the idea is we look at a value that comes from the pixel, or maybe from the neighborhood of the pixel, and based on that value, we decide what to do. We decide whether to do something or not to do something. Okay? We don't have to use only the information that comes from the pixel. We could use information that comes from somewhere else. For instance, we could use information from the clock of the computer, or information that comes from a website, or information that comes from the user. Point is, we have some value that we're testing against some other value. We're testing it for equality, for not equality, for less than, for greater than. And based on whether it passes the test or not, we do or do not do whatever is specified in the body of the loop, not the loop, of the if statement. So the author of the slides is suggesting that we could be using information like the color of the pixel to decide whether to do something or not. We could be using the location. We could be using the number of neighbors. I suggested that the number of neighbors can help you determine whether a pixel is in the corner. So for instance, if you only wanted to change the color of the pixels in the corner, you could look up the number of neighbors. And if it's 3, well, then it's a corner pixel. And so you can do something on it. There's probably easier ways based on location, right? If it's in the corner, then it will have certain values of X and Y. But looking at the number of neighbors would be legitimate. Okay. So back to some coding exercises, because that's the point of today's lesson, to write a lot of code. We want to draw a purple diagonal in our beautiful x.png, right? x.png, black background, white X on it. We want to change the diagonal that goes from the bottom left to the top right and make it nice and purple. Can I enlist somebody to do this for me? Because I'm feeling very tired after having written code all day. Okay, I don't have a volunteer. That is scary. Does that mean that everybody got scared with my explanation of if statements?
We understand it. We just don't know how to write it out.
All right. So I'm tempted to just copy and paste it out of my out of my scrapbook here, and that's exactly what I'll do. But then I'll explain it. There you go. And here's a beautiful purple line.
Whoa.
Okay, so let's take a look at my code. First of all, I am religious about using let when I create a variable. So I'm starting to add it even when we read the image initially. So let image is equal to new simple image, x.png. We're reading the file from the website, setting the zoom. And then I need information about the width. I don't really need information about the height. So we could delete this and it would be just fine. But I need information about the width. Okay, let's run this. Same as before, nothing happened. And then I'm doing some math in order to decide whether I want to change the color of the pixel or not. So for every pixel in the image, do the following. Okay, so now we have a pixel, right? When we are executing. What's that? Go ahead. There was a question coming and I didn't hear all of it. So I'll just continue.
Why is there like this white line going through the purple diagonal?
Well, check this out. Let me take away my code, right? So now the for loop isn't really doing anything. Run. There you go. That's the original image. That's what it was,
Okay.
at the beginning. That's x.png. So I'm trying to change x.png from a white x on a black background to be whatever it is, plus a purple diagonal that goes from the bottom left to the top right.
Okay.
And there you go. That's the diagonal superimposed on top of the original image.
Yeah, thanks.
No problem. So the trick here is I have to find a way to determine whether a pixel is on the diagonal or not. That's where all the ingenuity is here. Crafting a Boolean condition that determines whether the pixel is on the diagonal. I'd love to have a function, pixel dot is on diagonal, open parens, close parens, that just tells me. But there is no such function, right? What the pixel can tell me is its x coordinate and y coordinate. Now, if I have the x coordinate and y coordinate and I know how big the image is, I ought to be able to determine whether the pixel is on the diagonal. And so how am I doing this? I'm using this fancy math. I'm taking the x value of the pixel, and I'm taking the y value of the pixel. And interestingly, x and y are measured in a somewhat, unorthodox way. X increases from left to right, which is normal, but y increases from the top to the bottom in computer science or in images. Why? Nobody really knows. Does it make sense? Probably not, but that's just the way it is. So this pixel up here, top left, is 0, 0. Okay, 0 on the x coordinate, on the x-axis, and 0 on the y-axis. This pixel up here, and there's 10 pixels. This is a 10 pixel by 10 pixel image. So this pixel is not going to be 10 because this one was 0. So how many, if you count 10 numbers starting from 0, what's the last number that you will hit? Let's try that. Okay, I'm going to count 9, right? Let's do it for every, for the benefit of everybody. I'm starting to count from 0, and I'm using my fingers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when you count 10 starting from 0, you get to 9. So up here, the pixel is going to be x is equal to 9, and y is still equal to 0. Now down here, x is equal to 0. What's the value of y? Well, the value of y, if we were in a math class, would be -9, but in computer science, it's +9. So what I'm looking at is if I add x and y, here I get 9. That's 0 plus 9. And here, I still get 9. It would be 9 plus 0. But either way, I get 9. And 9 happens to be the width -1, right? The width is 10. subtract 1, get 9. So the instruction that I'm using, the condition that I'm using to determine whether a pixel is on the diagonal is to check for the 9-ness of the sum of the coordinates. So pixel get x plus pixel get y is equal to 10 minus 1, yes or no? If the answer is yes, then I proceed and do this. I'm setting the RGB values to some red, but not all red, no green, and a lot of blue. And a little bit of red and a lot of blue makes purple. Does that make sense?
Yeah.
Great. Let's move on. Now, we want to determine whether a pixel is on the border of the image. Okay, we want to write code that will change the border of our x.png image from black to green. Here, too, we will use a condition that looks at the x and y coordinates. But now, I really have to ask different questions. I have to ask the question, is the pixel on the top row? Is the pixel on the bottom row? Is the pixel on the leftmost column? Is the pixel on the rightmost column? There are really 4 different questions that I'm asking. Okay, I can't really ask a single mathematical question that somehow gives me all the pixels of the border, right? That is true for all the pixels of the border. So I'll have to use 4 different conditions. However, as you recall, the if statement only takes one condition, right? This is one condition. I can't give an if statement more than one condition. So what I need to do is I need to combine different conditions. And I can do that using Boolean operators. Boolean operators, we mentioned very briefly, I think in lesson number 1, we were talking about logic gates. Well, logic gates, like the AND and the OR and the NOT gate, and the XOR and the NAND and so on, those are Boolean operators. So the AND operator is an operator that returns true when both its operands, or both its arguments, are true. True and true is true. True and false is false. False and false is also false. And the opposite of that, or the complement of that, is the OR operator. That is true when at least one of its operands is true. So true or false is true. False or false is false. Okay, so here I can use either and or, some combination of Boolean operators to combine all the conditions that enable me to determine whether a pixel is on the border or not.
Less than.
What was your comment?
Could you do less than 9 if the number of neighbors is less than 9?
Oh, we could do that too. Yeah, that's clever. So actually, why don't you screen share and do it yourself? And that's what happens when you speak up during a lesson. You get called on.
Okay.
Let me unshare. Hopefully you can share now. There were some problems earlier.
I still can't share for some reason.
Huh. I'd love to be able to.
You don't, Mark, if you don't believe me, you can come here, Mark. Look. My entire screen.
Boom. Boom.
Okay, thank you, Mark.
Okay, that was clever.
Okay, so it would be this thing. Where are we? We are, wait, we're on making a border.
Yep.
So would probably need a for loop.
Remember how to read a for loop? You want to write something that means for every pixel in the image. And how do you write for every pixel in the image? And then you need the open squiggly brace.
Oh wait, I forgot
Okay.
the curly.
Curly brace. And then you need an end curly brace at the end of the block.
Yep.
Okay, and then you can write your code in there.
Yeah, it's a good habit to write the open and the close at the same time so that you don't miss it later, especially when you're writing very complicated loops. Just open, close, and then insert your code in the middle. That's the right way to do it.
Okay. You need the usual squiggly braces after the if statement.
Oh yeah, I forgot about those. Can you guys see that?
We can. That is
Okay.
surprising. That is surprising. So I'm surprised because we said that the number of neighbors for an ordinary pixel is 8, right?
Yeah.
So for some reason, count neighbors is also counting the pixel itself. I had not noticed that, but that apparently is what it's doing. It's counting the pixel plus all its neighbors. And so you've been very clever. With a single instruction, you have, or with a single condition, Boolean condition, you have captured whether the pixel is on the border or not. I want to show you. What's that? Sanjay, you're saying something?
That's very clever. That's a really
Clever.
good way, because the observation was that every other pixel had, eight neighbors, right? Or that's basically what it was.
Yeah.
So very nicely done.
Excellent. Excellent. We will send you a gold star for your, to put on your T-shirt. Let me show you. Okay, you can make it red. Let me show you an alternative way. Not because it's any better, but because it allows me to show an alternative way that is also important, which combines different conditions together. Okay, did I do this right? Probably not, and I can't stay on the same page to save my life. Okay. And there you go. We have the purple border. Why purple? It was supposed to be green. Doesn't matter. I made it purple. Look at how I'm doing it here. I am asking the pixel, what's your X value? What's your Y value? And then I'm using the X and Y values to determine whether the pixel is on the first column or on the leftmost column or the rightmost column, on the top row or on the bottom row. X equals 0 means is the X coordinate 0, yes or no? Where is the X coordinate 0? The X coordinate is 0 on the first column. Right here, do you see my mouse? This is where X is 0. And then I'm asking, I'm also asking the question, is X equal to width minus 1? Width is 10, minus 1 is 9. So is X equal to 9? Yes or no? Where is it equal to 9? Here, rightmost column. And then I'm asking, Y equal 0. Where is Y equal to 0? Topmost row. Where is Y equal 9? Bottommost row. Now I have 4 different conditions. And I need to combine these conditions in such a way that if at least one of these conditions, if even just one of these conditions is true, then the whole combined condition is also true. Well, that's what the OR operator does. Okay, true or false or false or false is true. True or false is also true. But I'm happy with having just, do I have somebody trying to join? Looks like somebody's trying to join. I'm ignoring them. Sorry about that. So these double vertical bars, also called pipes by programmers, these double pipes are an OR operator. The double pipe is the OR operator. So I'm basically saying, is x equals 0, or is x equal to 9, or is y equals 0, or is y equal 9, yes or no? If any one of these conditions is yes, then the whole condition is yes, and we execute pixel.setRGB. And there you go. We get the purple border. So this starts getting fancier. This is where we add another little piece of the puzzle, the else clause. So we have the condition. In the if statement, we have if condition, the body, and then we have the else clause. The else clause is executed if the condition is false. So in the if statement, we can both do something when the condition is true and something else when the condition is false. Good? It's 7:20, and I might propose leaving these two pages for exercise, for homework. What do you think, Sanjay?
Sounds good to me. I mean, you guys want to go for like another 5 minutes and finish it up? At least finish one of them?
Image detection. Okay.
Was that?
Actually, never mind.
We have time.
Okay.
Yeah.
Hang on for a second.
Alex, how are you doing? Are you super tired? Or are you okay?
Yeah, give me 1 second.
Okay.
Okay. Do I have the code for this one? There you go.
Some of the kids are in Texas, but they're still going strong. Good job, guys.
Excellent. Okay. There it is. So let's read the instructions again. Write code to make a purple diagonal line running bottom left to top right and color the rest of the pixels green. So basically, we are completely overwriting the original image. Okay, we're doing something to every pixel. So we're completely overwriting the original image. How do we do that? For every pixel in the image, and I use the same condition that I used earlier to determine whether we're on the diagonal, right? This condition here. If the sum of the x and the y coordinates is equal to 9, with -1, which is 9. So that gives me, that's true. That condition evaluates to true for all the pixels on the diagonal. And so for these pixels, I can set them equal to 200, 0, 255, which is purple, right? We saw that that's purple. Otherwise, so if we haven't set the pixel to purple, then we want to set it to green. There you go, right? So if condition is true, then do this, else do that. Does that make sense? Readable enough? Let's try something just a little bit different. Maybe we, instead of setting the RGB of the pixel in the else clause, so instead of overwriting the background completely, we will just set the green to 255. Set green to 255 and not touch the other two colors. Now we can see that we are preserving the white pixels in the background, or not in the background, the white pixels that formed the cross, the original cross. Why is that being preserved? I don't have a condition that does anything special with those pixels. So, I'm setting green 255 to every other pixel that is not on the diagonal. So why are we getting white on those pixels? The answer is we're getting white because white already contains a green value of 255. So, and I'm not touching the other colors now. I'm only setting the green to 255. So the pixels that are black become green, but the pixels that are white stay white. Good?
Yeah.
Awesome, man. That's
Okay.
really cool.
So I don't want to give the edge detection algorithm as homework, though I encourage you guys to try it. Combining conditionals, we've already seen. I wanted to show the OR operator, the double bar, or double pipe as it's called, and the ampersand, which means and. So I've shown you that as an example. You should be able to execute this exercise, to do this exercise by yourselves. So I'll leave this to you. I will do edge detection, I guess, tomorrow. But I encourage you to try it. Okay, it's very interesting. Okay, I will
Everyone good?
stop recording.